Alright, in this video, I want to run through a practice problem of what I kind of judge as a moderate difficulty electric dipole practice, problem. You might see variations of this, there are many hundreds of types of problems, but understanding the conceptual reasons helps. And I think the first step in understanding is to see someone's thought process so that you can sort of emulate and then slowly build your own intuition. And so without further ado, let's define this problem. So the question is, what is the angular velocity max in this scenario? And so first, what is this problem? Well, we have an E field, so an E field going towards the positive y direction, and we have an electric dipole kind of situated at some angle phi from, and the angle phi is defined from the positive y-axis to the positive x-axis, so in this sort of curling direction. And the question is, again, what is the angular momentum max in this scenario? And so I encourage you to solve this problem. So answer everything in constants, so just assume the charge is Q, E for electric field. Don't use any numbers unless it's like 1 over 4 pi epsilon naught, or so on and so forth. So if you gave it a try, let's see if you get the same solution as I do. And there's always a chance that my method is not the most efficient, but it's the one that makes the most conceptual sense to me. And so first, when I'm thinking angular max, I'm thinking of the kinetic energy definition for angular, the angular kinetic energy definition. That is 1/2 over moment of inertia times angular velocity squared. And then conversely, I then think that maybe I can think of delta K, so the change in kinetic energy, is equal to negative change in potential energy, or work. Either way, both work. Both work. So let's think. At the initial position here, right? And so, well, first we actually have to think, what is the point where we will have an angular momentum max, right? So the E field is running positive direction, and this dipole is kind of situated in between. If I turn it this way, right, it would be anti-parallel to the dipole, right? This positive charge will be opposite to this direction, and that means that it probably isn't going to move that way, right? It has the natural tendency instead to move in this direction, right? And so the work done by the E field will go kind of curling in that direction. And so we can expect that the angular max, or even kinetic energy max in that scenario, is going to be parallel to this E field, right? So now that we understand that, we can think, what is the initial, right? So in our initial value would be, so 1/2 I, so angular max squared, right? So that's the final position minus the initial, so 1/2 I angular initial. So, and the initial will be based on phi, so I would actually call this angular phi squared, right? So if the initial was over here, right, you can calculate that using, your given knowledge. And so what is negative potential energy? So recall that our potential energy value is defined as, or actually let's write this over here. So potential energy is equal to negative P E cosine phi, right? So that means that we can define as U1 minus U2 here, right? U2 being where we have potential energy that is higher, right? Because if we have an increase in kinetic energy, then we would get a decrease, right, in potential energy. So we can say negative PE cosine of phi 2 minus negative PE of cosine phi 1. Oh, well, actually I got the angles messed up. So it's cosine phi 1 here, right? Minus so to understand this really clearly, let's make sure we know what we're talking about. Phi 1 is the smaller angle, right? And if it's directly here, then it would just be just PE, right? Just PE. And for here, it would be minus negative PE cosine theta 2. So let's pause. Let's think about this conceptually again. Recall, this is the smaller angle, so less potential energy when kinetic energy is at a max, right? And more potential energy when kinetic energy is at a smaller minimum, right? So actually I should put theta 2 there, right? So this makes sense, right? This maximum, so this is U1 minus U2, right? So don't get crossed up by these negative signs, right? This is a whole term. This whole term right here, including the negative, is U1, or essentially U minimum. You can think of it that way. So actually, let me just leave those here, U2. So let's rewrite this. 1/2 I V max squared minus 1/2 I V max, or U2, equals, and then these two negatives cancel out, so we can write this PE cosine of theta 2 minus PE cosine theta 1. And so here you just do some algebraic manipulation, so we move this to the other side. So then we get 1/2 I V max squared is equal to PE cosine phi 2 minus PE cosine phi 1 plus 1/2 V max, 1 squared. Now, if you notice here, I forgot to mention this before, if there is no kinetic energy to start off with, so we're assuming basically like somebody's holding this dipole in the E field and then they let go, right? We start off with initial 0 kinetic energy, and so, or 0 angular momentum and so on and so forth. Or not angular momentum, angular velocity. So in that case, this would cross out to be 0, and this would be far simpler. But if it is the case that you are given a kind of an initial, right, so we're not actually calculating from stationary and then let go into the E field so that it rotates from here to being parallel, you wouldn't be able to assume that. So that's why I left this here. It's a general solution. So let's continue our algebra here. So move the 1/2 to the other side, or move the 1/2 to the other side, so multiply the whole thing by 2, and then divide by I, right? And then square root. So that becomes V max. So the angular velocity max is the square root of this really big thing. So 2 times PE cosine phi 2 minus PE cosine, oh geez, I forgot a C, cosine phi 1 plus 1/2 I V max phi, that's not phi, that's supposed to be phi 2, phi 2 squared, divide, and all of this multiplied, so 2 times that whole thing, divided by, oh geez, divided by the moment of inertia. And that would be our final answer. So it's a bit sloppy here, but hopefully this makes sense, right? So let's go back to the beginning again. We have changing kinetic energy, and theta 2 is this bigger angle, so theta 2 is like this, and then theta 1 will be like this, right? And so, you know, the problem could be different numbers. I'm trying to solve a general solution, right? This is a conceptual solution, and that is what's most important in physics, or at least my opinion is that if you can get the conceptual and the math, then number plugging is an easy game. So again, potential energy is negative PE cosine theta, and the kinetic energy is equal to negative change in potential energy. So the smaller angle first, right, because there'll be less potential energy there when kinetic energy is at a maximum, and then it'll be negative PE cosine phi 1 minus negative PE cosine phi 2. So when potential energy is at maximum, this is at a minimum, and then that's U1 minus U2. Conversely, if you look here, this is just work, right? So really, if you're not comfortable with understanding this negative change in potential energy, you could just set up everything in terms of work. But I encourage you to conceptually understand this. And then one last thing is that the true maximum here, right? So I encourage you to pause right now. The true angular velocity maximum would be when it's parallel, like right when it swings over parallel to the E field, that is its maximum. And so in that problem, there could be a problem where you have, you know, initially you have no angular velocity, so that would be 0. And then you are solving for when this is maximum, and that means that your final angle would be 0, right? So your theta 1 would be 0. That means your smaller angle would be 0. So this whole thing would equal to 1. And so that's one type of solution. But again, we have the general solution. We can solve anything similar to this. So I hope that helped, and see you in another video.